Okay, I'll start now. For those of you who haven't been in the KSET sessions, I'd just like to introduce myself. My name is Vidhu, and I'm a final year student at the Department of Physics in the JB campus, okay, from Bangalore University. So I'll be discussing about 10 net questions today, okay? So let's see how this goes. Okay. Okay, so the first question here I have is, okay, I want to calculate the value of the integral, okay, along this open contour in the complex Z plane, okay? So this is not a closed contour, this is an open contour, okay? So what I will do is I will make this a closed contour, and then I will subtract a couple of functions that I have at this point and this point, okay? So I will tell you how this is done, okay? So the value of the integral C dz z square e power z, where C is an open contour in the complex plane Z, is as shown in the figure below. Okay, so this is your real axis and this is your imaginary axis. Okay, and these are the options that are given to you. So let's look at what we have to use. Okay, so we have to recall this from memory. Okay, we've done this Cauchy's integral theorem in our BSc. Okay, we've also done it in our MSc again. Okay, so what we're going to look at here is a closed contour. Okay, okay, so your C is a closed contour here in this theorem, but in the question it is an open contour that we have. Okay, we have an open contour. So okay, so if your function f of z is analytic in some simply connected region, okay, so let me just brief you through what you mean by simply connected region. Okay, so the thing is that these kind of regions which can be drawn to a point, okay, so basically you can take this regions outside and shrink it to a point, okay, those kind of regions are called simply connected regions. When you take this kind of a curve and try to shrink it to a point, it does not, okay, so it basically shrinks to 2 points, and this one cannot shrink to a point because of the hollowness that's inside. Okay, so these kind of curves are the only curves where you can apply this theorem. Okay, so if you're looking at a contour which is not simply connected, you cannot apply this rule. Okay, so for any closed contour C contained in your region R, this is a closed integral. That's why this is represented with a ring in the integral. Here, if you look at it, this is like an open contour. Okay, so it's just this part. Now let's actually go on to use that to solve the problem. Okay, so let me look at this. Okay, if your f is a complex antiderivative of your little f, that is your function. So antiderivative is basically the integral of your f. Okay, so this simply means it's the integral of f. Okay, so that's what's antiderivative. So if that is the case, you evaluate the integral at one point of the curve and subtract it from another point of the curve. Okay, so let's go back to the figure. Okay, what do you have here? This is the starting point A, okay, and this is the end point B. So what do? You evaluate the antiderivative at A and you evaluate the antiderivative at B. Okay, so if I want to compute this region's integral, all I have to do is integral of C f of z dz is equal to, I subtract this, okay, so f of b minus f of a. Okay, so you should make sure that A is the starting point and this is your end point. Okay, so that's basically something that is that uses the Cauchy's integral theorem, and then you end up getting this kind of a formula. Okay, so this is obtained from your Cauchy's integral theorem. Now what do? You have to try to compute the integral z square e power z dz, right? So what you try to, I feel like the Bernoulli's integration formula is the easiest method to compute the integral. So I'm going to be showing you how to do that, okay? So let's look at this. You have a u dv is equal to u v minus u prime v1, u double prime v2. So all the u's are basically the derivatives and v's are basically the integrals that you have. Okay, so the first function that you have, what do? You basically use an isolate rule that you have. Okay, so you have an a here and you have an e here. So a stands for your algebraic function, e stands for your exponential. So you put it in that order, z squared e power z, and integrate it. So let's do this. Okay, so z squared, you just leave it as such, and when you integrate this e power z, note that it's du here and not just dv here, not just v. So you have to integrate this once, then you have to subtract it, and then you get 2z and v1. So you get an e power z again when you integrate it. Okay, and then you have a plus, take this one's derivative, so you have a z and e power z. Okay, so this is how you're going to be getting your integral out. Okay, so let's just look at this. Okay, so that's your integral. Now what you have to do is, this is your antiderivative or your integral. So you evaluate this antiderivative at this point A and the point B, and then you subtract both of them. Okay, so you evaluate it at the point A. Now you have to be careful about this. If you look back at your figure, okay, if you look back at your figure, you basically have just your real parts. Okay, you do not have imaginary parts. So it's fine as long as you substitute the value of just x. Okay, so basically you have z is equal to x plus iy. So what is happening here is your y is 0. So this term goes away. So z is equal to x. So you can just directly substitute this value of 1 wherever you find z. And similarly, you can substitute this value of -1 for the other endpoint that you calculated. Okay, so let's look at this. Okay, so you just have to substitute this f of a. Okay, so here you see it's z. Okay, basically this reduces to e power x squared minus 2x plus 2. Okay, because your value of y is 0 in the real axis. Okay, in the real axis your y is 0, so you just have to substitute this. Now, okay, so you substituted that. Now what are you supposed to do? You're supposed to put this value of e over here. Okay, once you've substituted the value of 1 and -1, you find out this and put the value of f of b here, that is 5 by e, and subtract it from this. Okay, so you have 5 by e minus e. Now let's just go back to the options and check it out. What is it? It's 5 by e minus e. So it's option C. Okay, so let's move on to the next question. Okay, which of the following matrices is an element in the group SU2? Okay, so the special unitary group 2 has a property, and I will show you what the property is, and it's just learning that property that applies over here. Okay, so these are the options, these are the matrices that are given to you, and you need to check if this particular matrix is an element of this group. Okay, so the SU2 group has a particular property here. Okay, so SU means special unitary. Okay, so SU2, basically n gives you your degree. So this is your special unitary group of degree 2, and this is how it's defined. So let's look at this. You have an alpha here, you have an alpha bar here, that's your complex conjugate. Okay, you have a beta here, you have a minus beta bar here, which is again, whenever there is a over bar, it's basically a complex conjugate. Okay, so both of these alpha and beta should belong to your complex numbers, and alpha squared plus beta squared, the modulus of both of them should give you 1. Okay, so modulus of alpha squared plus modulus of beta squared should give you 1. Okay, so let's look at this. One of these things that was given. Okay, so let's rule out some options. Okay, so here you have these two same, fine. Here you have, okay, so these two have to be, these two would be same if they are real numbers. Okay, let's look at this one. Okay, so here you have a complex conjugate. Okay, so here you basically have alpha, and this is alpha bar. Okay, if you look at this beta, okay, you know that real numbers are also included in complex numbers, right? So this, even this can be minus beta bar. Okay, so there's no complex quantity here, there is no I here. So what you do is you just put a negative of the real number. Okay, So now let's just go on to this. Okay, so you have an SU2 alpha minus beta, beta and alpha bar. Okay, and then this is what you need to show. Okay, so what do? You take this quantity and you square it. You take this quantity and you square it, and then you end up with a 1. Okay, so these kind of matrices which you have, which end up when you square these alternative terms, okay, this term and this term, and if it ends up giving you a 1, then you call it a then you say that this matrix is a element of the SU2 group. Okay, so these have these special unitary groups are extensively used in particle physics. Okay, so yeah, I'm not going to elaborate on that because there are a lot of second semester students here, like students who just finished their second semester, and they haven't taken the nuclear elective. But you will see if you take the nuclear elective, you'll see that SU2 has a lot of applications. Okay, so the symmetry that is due to SU2 has a lot of great application, great results that has come out. Okay, so basically what your SU2 does is helps you understand electroweak interactions. So electroweak interactions are basically when you have you basically have these 4 fundamental forces, right? You have gravitational, electromagnetic interactions, weak interactions, and strong interactions. So out of those 4, 2 of these interactions, basically your electromagnetic interaction and your weak interaction, are basically, you know, combined in a way. Okay, so what you realize is when you kind of like apply these onto these particular SU2 transformations onto this, okay, SU2 group onto a particular thing, you basically find out that these kind of systems do not change. I mean, the dynamics of the systems do not change. Okay, so that's just something extra that I wanted to say about SU2. It's not really relevant to this problem here. Okay, so let's look at this question. Let A and B be 2 distinct 3-dimensional vectors. Then the component of B that is perpendicular to A is given by. Okay, so this is a problem from your vector algebra section. Okay, so it's pretty simple. Okay, all you have to do is, let's say you have 2 vectors A and B. Okay, so let's take their cross product and you have A, B sine theta and cap. Okay, after that, what do? You kind of like take a dot product. Okay, so let's look at this carefully. Okay, so A and B be 2 distinct 3-dimensional vectors, then the component of B that is perpendicular to A. Okay, so if you have 2 vectors like this, you have a vector A and you have a vector B, you want to find out the component of B that is perpendicular to your A. Okay, so basically you want to find out this part over here. Okay, so you know that is B sine theta. Okay, you automatically know that is B sine theta. So let's just try and compute it from here. Okay, so I will do an A crossed with A cross B. Okay, so let me see what I get from that. So I will do an A vector. Okay, so if I look at this, basically let's look at it this way. Okay, I will kind of like erase this part, erase this end cap, and let me say that these 2 A and B are lying on this plane. So then when you do your cross product, you get it out of the plane of papers, so that's a K cap. Okay, it's coming out. So now when I take this A and I take a product with your A cross B, what do I get? So let's look at this. So A is along the x-axis. Okay, so I will put this as A I cap. Okay, and I'm crossing it with this quantity that I've already found, A B sine theta and K cap. Okay, so I will take this, I will write A squared B sine theta, and I have an I crossed with K. Okay, so you know when you're doing an I crossed with the K, you're supposed to be going cyclic, right? I, J, and K. Okay, so when you end up getting a cyclic order, you can say that you can get I crossed with J is K, K crossed with I is J, and so on. But here you see you want a reverse order, I crossed with K, so you end up putting a minus J cap. Okay, and this quantity that you have here, this negative sign can be shifted to this side. Okay, so I have a minus A vector crossed with a vector crossed with the b vector is equal to a squared b sine theta k cap. Okay, sorry, j cap, because your I cross j, I cross, just a second, your I cross k was minus j. So let's put that as j cap. Okay, so now what I can do here is I can use the property of commutation, anti-commutation. Okay, so basically when you're looking at your cross product, the cross product is anti-commutative. So I will have a crossed with b crossed with a, okay, divided by a squared is equal to b sine theta j cap. So basically when you're looking at this b sine theta, let's just have a close look at this diagram. Your j cap is along this direction, right? So this was b sine theta j cap. Also, you're supposed to be finding the component of b that is perpendicular to a, okay? So that's why you end up having something like this. Perpendicular to your x-axis is your j cap, okay? So the option is this, okay? So option A. Okay, so this is your diagram. This is what I talked about already, okay? So the calculations are kind of like extensively written down here, and this is what you have as your final answer. Okay, so let's look at this carefully. Okay, this is a very simple question if you look at it. In fact, they've actually given you all the details that you need in the question itself. Okay, so all you have to do is read the question carefully sometimes. Okay, so because they've given you all the things that you need or the information that you need in the question itself, these are very easy to kind of solve. Okay, so let P of n of x, where n is equal to 0, 1, 2, 3, be a polynomial of degree n with real coefficients defined in the interval 2 less than or equal to n less than or equal to 4. If your integral from 2 to 4, Pn of x, Pm of x is equal to your Kronecker delta, okay, delta Mn, then, okay, what is P0 of x and P1 of x? So they've given you P0 of x and P1 of x, okay? So what is the definition of your Kronecker delta? The definition of your Kronecker delta is basically if m is equal to n, then your delta mn that you have will be 1. If m is not equal to n, then your delta mn that you have will be 0, right? So all you have to do now is take a P0 of n and P0 of x, P0 of x integrated from 2 to 4 and check if you're getting 1. Okay, if you're getting 1, that is a correct version of P0 of x. Then what do? You take your integral from 2 to 4, P1 of x, and okay, P0 of x and P1 of x, and then you check if you're getting a 0. Okay, so if you're getting both these things, then that is the option. Okay, now let's kind of like rule out certain options that we have here. Okay, so basically, if you have a negative sign that's coming up, okay, if both the signs are going to be negative, then your integral is not going to be 0. Okay, so if you take a product of these two, the integral won't be 0 because both sides are negative. If you have both signs positive, it's not going to give you a 0. So only when you have a mix of both positive and negative quantities is it going to give you a 0. Okay, so this is not an option, so we can rule it out. This is not an option, so we can rule it out. Now let's check this out. Okay, so you have a 1 divided by 2 here, right? So if you have an integral from 2 to 4, 1 divided by 2 into 1 divided by 2 dx, okay, what do you end up getting? You end up getting a 1 divided by 4 integral from 2 to 4, okay, and you integrate 1, right? So you end up getting an x divided by 4 in the limits of 2 to 4. Okay, so you substitute 4 divided by 4 minus 2 divided by 4. What do you end up getting? You get a 1 here, you get a 1 divided by 2 here, you get you half. Okay, so you're not getting this result. Okay, so you're not getting this result. That means this is the answer. Okay, so this thing I've kind of like worked it out elaborately in the next slide. Okay, so let's look at this. Okay, so basically what do? You integrate and see if you get a 1. And then you substitute m and n to 0 and see if you get your delta 0, 0 is equal to 1. Okay, so this is your Kronecker delta that you have. And then you kind of like try and integrate this. Okay, so here I have used the fourth option that I have. I kind of like used P naught of X is equal to 1 divided by root of 2. And then I have done this. Okay, so I multiplied this twice because I have a P0 of X and P0 of X. I realize I'm getting a 1. Okay, so that is a good thing. Okay, so that means one of the part is like coming true. Now, if you do not have time, you automatically tick off the fourth one. Okay, so if you do have time and you have time to verify the question, you can kind of like do P naught of X and P1 of X. Okay, so you multiply it and then you integrate it. So this is a trivial integral. You can just kind of like do it immediately. You have a root 3 divided by 2, and then you have a 3x minus x squared divided by 2, and the limits from 2 to 4, you end up getting a 0. Okay, so you end up knowing that the final, the last option that you have, option D, is the correct answer. Okay, so let's look at this question that we have. Okay, this question has a little bit of trick to do with it. Okay, so whenever you see analytic functions, the automatic reaction is to kind of like do the CR equations, the Cauchy-Riemann equations, and then check if that is going to be valid. Okay, so here there is kind of like a trick to do with it instead of working the whole thing out. Okay, so which of the following is an analytic function in the complex variable z is equal to x plus iy in the domain modulus of z less than or equal to 2? Okay, so these are the options that you have. Now, let's just look at this one particular function. Okay, so if your f of z is equal to x minus iy, okay, so let's just see if the CR equations are valid for this one. Okay, so CR equations, the Cauchy-Riemann equations, let me just put this as u, okay, minus I v. Okay, so dou u by dou x is equal to dou v by dou y. Okay, that's the first CR equation. Let's see if that is valid. So if I do a dou u by dou x, my u is equal to x, I get a 1. But if I do a dou v by dou y, okay, so this has to be a negative sign here. Okay, so this is minus v is actually minus y. Okay, so here what you end up having is minus 1. Okay, so minus 1 is not equal to 1. That means your CR equations are not satisfied. So whenever you have a z bar, okay, so that is your complex conjugate of your z in any of these equations, those are not analytic. Okay, so if you have your CR equation, I mean, if you have a z bar, a complex conjugate, okay, in any of these equations, this is not going to be an analytic function. So let's check this out. Okay, so you have an x minus iy, that means you have a z bar. Okay, so if you have an x minus iy, what do? Okay, so this is not an analytic function. Next, let's look at this one. Okay, so here you can take out this minus sign and you have an x minus iy, right? So let's cancel this out. Okay, now this one, when you pull out the negative sign, you have an x plus iy. Okay, so that can be. Okay, let's just put can be. And this one, let's look at it again. So this, I will tell you why. Okay, so let's just erase this off. Okay, so yeah, okay, so this, let's look at it over here. Okay, so there is a power that you have. Okay, so whenever you have functions, let's say root of z, z power 1 by n, sine inverse of z, or log of z. Okay, so these functions are basically multi-valued functions. Okay, so multi-valued functions. Okay, so you have multi-valued functions. And what do we do when we have multi-valued functions? So basically, let me just explain it to you. I give you one input, okay, and let's say this is your function f of z. Okay, so this is z is basically the input. I get several f of z's for a particular input. Okay, so those kind of functions are basically multi-valued functions, and they have a couple of branching points. And what you do for them is basically, you won't be able to find the analyticity of those kind of things. Okay, so what you do is you take a, say you have 2 points that are there. Okay, so let's call it a branching point. Okay, let's call that a branching point that you have. Okay, so what we do is basically we evaluate it at one branching point. Okay, one branching point. Okay, so let's look at this root of z. Okay, so when you have root of z, if you kind of like try to evaluate the function, you have both positive and negative things coming out. Okay, so in that kind of a situation, you either look at the analyticity at just one positive value of the function, or you look at the analyticity at just the negative value of the function. So if you try and look at both points, it's not going to be analytic. Okay, so they asked for which of the following are not analytic. So we've kind of like decided that this is not analytic, this is not analytic. Now, because you have a root over here, this is not going to be analytic because they have multiple branching points. So this is the answer. Okay, it's option B. So let's look at this. Okay, so this is just a kind of like a recap on the Cauchy-Raymond equation. So you have a dou u divided by dou x is equal to dou v divided by dou y, and dou u divided by dou y is equal to minus dou v by dou x. So typically your u and v are real and imaginary parts of your complex function. Okay, and this is how you basically define the function itself. Okay, so let's look at this. So let's look at the points. Let's just review the points again. If z is equal to x minus iy appears anywhere in the expression, then it is not analytic. Okay, so you can check for this guy, which we kind of like done for this particular function. We kind of like checked with the CR equations and we found that it is not analytic. Now you look at your option D. Okay, so you have branch points because the power is root. Okay, of 1 by 2. Okay, so you basically have a root. So these kind of functions which are multi-valued, okay, or root of z, z power 1 by n, log of z, root of z minus a, sine inverse of z, all these kind of functions are multi-valued functions. So these kind of functions are not analytic. Okay, so for these kind of functions, what you basically do is you check the analyticity at a particular branching point. Okay, so here you would have 2 branching points for your z. Okay, here you would have n branching points. So you just check the analyticity at that particular branching point. Okay, so let's go on to this question. Okay, so consider the matrix M equal to 1, 1, 1. Okay, so these are like 1 everywhere, and the eigenvalues of M are what? Okay, so I think I told one of these tricks to the KSET classes while I was taking it. Okay, so for the KSET sessions. Basically, when you're looking at this kind of a matrix, you calculate the determinant, okay, and you calculate the trace. Okay, so if you calculate the trace here, it's 3. Okay, so trace is the sum of all the diagonal elements. So your trace of your M is basically equal to 3. Okay, so let's look at all of this. All of these have 3. Okay, so this is minus 1 plus 1, 3. All of these are 3, so we can't do anything with that. Now let's check out the determinant. Okay, so if your determinant is the same as the if your determinant is the same as the product of the eigenvalues that are given to you, then you can check that option out. Okay, so let's check out the determinant for this. Okay, so what I'm going to do is I'm going to kind of like show you another method called the sources method. Okay, how to kind of like quickly calculate determinants for the 3 by 3 matrices. Okay, so what I'm doing here is basically I wrote this matrix down and I repeat these 2 columns again here. Okay, so I repeat those 2 columns and then let me do this. So I have a 3, and then when I multiply this, I have a 3, and then I multiply this, I have a 3, and then I subtract it. Okay, so now I'm going to go upward. This was downward, now I'm going to go upward. So I multiply this, I get a 3. I multiply this, sorry, this is not 3. Okay, when I multiply it, I get a 1. Okay, so let me erase all that. Okay, so I multiply all of them, I get a 1, 1, 1. So 1 into 1 into 1 is 1 again. Okay, so that kind of repeats on, and then I get 1 all over here. Okay, so for all these values. So what do I get? I get a 3 minus 3, and that's giving me a 0. So that too is not going to be sad enough because I have 0 into 1 into 2 here. So when I take the product of these eigenvalues that I have, I end up getting a 0 here. I take the product of these eigenvalues, I end up getting a 0 here. Okay, so the idea is if you can kind of like do these two things, okay, do these two tricks and use those two tricks to see if these two relations are true, okay. So basically you have the product of the eigenvalues here, you have the sum of the eigenvalues here, and if these two are satisfied and you can rule out options, then use them. Now, in this case, you can't do any of that, okay. So what you will do is you have to kind of like find out the characteristic equation, that is A minus lambda I, okay. So you have to do that whole process, or in this case, M minus lambda I, okay. So you have a 1 minus lambda, 1 minus lambda, and 1 minus lambda here, okay. So that is your characteristic equation. You take the determinant and equate it to 0. Okay, so even in this, you kind of can use the sources method to do it, okay. So let's just do that. You have a 1 minus lambda, 1, 1, 1, 1 minus lambda, 1, 1, 1, 1 minus lambda. Let's repeat these two columns again. So 1 minus lambda, 1, 1, and this one, 1, 1 minus lambda, 1. Okay, so let me just take the product of this. So I have a 1 minus lambda cubed. I take the product of this, so I have a 1. I take the product of this, so I have a 1. Okay, then I do a minus. Okay, so I take this one's product, I have a 1 minus lambda. This one's, I have a plus of 1 minus lambda and a plus of 1 minus lambda here too. Okay, so now what do I have? I have 3 times this. Okay, so let me just reduce that out. 3 times 1 minus lambda with a negative sign, and here I have a 1 minus lambda whole cubed, and I add a 2 to this. Okay, so this is what I have. Now what I will do is I have to find those eigenvalues out. Okay, so I will expand that 1 minus lambda whole cubed. Okay, and then I will find out the eigenvalues. Okay, so 1 minus lambda whole cubed is what? 1 minus, let me do lambda, this is lambda, okay. Then I have a plus lambda squared, okay. So I'm going to expand this. This is basically A minus B whole cubed that I'm doing here. And then you have this, okay. So let me just quickly calculate that out. So here I have plus 2, okay, minus 3, and then I have a plus 3 lambda, okay. So I've multiplied these inside the bracket. So I cancel this out, okay, because minus 3 and 3 from here. I cancel plus 2 lambda and minus 3 lambda out. So I'm left with these two terms. Now I can pull out lambda square. So I have 3 minus lambda is equal to 0. So 2 of the lambdas that I have are 0, and the other lambda that I have is 3. Okay, so this is your option that you have. So let's just go through it once more. Okay, so these are the shortcut methods, okay, but it doesn't apply here because the ruling out kind of like just rules out 2 options, it does not reduce it to 1. Okay, so you have a trace, which is the sum of the eigenvalues, and determinant, which is the product of the eigenvalues. Okay, so you use the Cayley-Hamilton theorem. The characteristic polynomial is given by your determinant of A minus lambda I. You equate the characteristic polynomial to 0 and find the eigenvalues, and then this is what you do. Okay, so this is the whole procedure that I've learned. Okay, so you end up getting 0, 0, and 3. Okay, so I'll move on to the next question. The exponential of the same matrix simplifies to, okay, I is basically your identity matrix and it's given in the options. So let's just look at the options that we have. Okay, so you have e power m is equal to I e power 3 minus 1 divided by 3 into m. Okay, and these are the several options that are given to you. Okay, so now what I will discuss about is projectors. Okay, so projectors are basically your idempotent matrices. What is the property of your idempotent matrices? It is basically you have something like this. Okay, you have an A equal to A square. Okay, so these are called the idempotent matrices. So this is a trick that is pretty much not there anywhere. Okay, so it's not there anywhere, and mostly what people end up doing is they diagonalize it. They use a similarity transformation, and that's like taking you something like about 3 to 4 pages to actually complete it. Okay, so this is a small trick that you can use. what you have to do is, this is not an idempotent matrix. So let's just take the product of this matrix. Okay, so what I said was A equal to A square is your idempotent matrix. So let's try to find out the product of this. Okay, 1, 1, 1. Okay, so now you have a first row, which is the first column. Okay, first row and the first column, you're trying to take the product. So you have 1 into 1, which gives you 1. Okay, so I'll just do the first one elaborately. 1 into 1, which gives you 1, 1 into 1, which gives you another 1, and 1 into 1, which gives you another 1. Okay, so you end up having 3, 3, 3 all over. Okay, so now how is it that I can get back this value that I have? Okay, so the only way to do that is to actually pull out your 1 by 3 from here. Okay, so let's just look at this. The only way you can get this is basically, if you want to make this an idempotent matrix, is to divide it by 3. Okay, so this matrix is an idempotent matrix. Okay, this is an idempotent matrix. So now let's look at, just a second. Let's look at this. Okay, so this is finding out the exponential of a matrix using the property of a projector. Okay, so I'm assuming that the matrix is a projector, and projector basically means A square equal to A. That means your matrix is an idempotent matrix. Okay, and what I will do is I will use the formula, okay, the basic formula that I have, exponential of, say, A theta. Okay, so e power x is basically equal to, I think you should know this, e power x is equal to 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, and so on. Okay, so I will be using that in this matrix. Exponential of A theta is equal to I plus A theta whole squared divided by 2 factorial, and so on. Okay, so this is basically a crushed notation. Okay, so it's a simplified notation that you have. Okay, and what do? Okay, so what I'll do is I will use this property of a projector. So what do? If I have an A square, I substitute it as an A. If I have an A cube, what do? I substitute it as an A square and an A. So that becomes an A, and then I substitute an A square again. So basically, if you have an A cube, you can write this as an A square and an A, which is equal to A, because your A square is equal to A. And then you end up having another A square. So that gives you A. Okay. So whatever multiples of that you get, you end up getting an A, and you can pull out your A. Okay, so you can pull out your A. So if it's an A power 2, it's an A. If it's an A, it's still an A. If it's an A power 3, it's going to be an A. If it's an A power 4, it's still an A. Okay, so you're going to pull out an A from that exponential term, and then what do? You write this exponential of A theta as I. You add and subtract an A. Okay, so that you can write this as an exponential e power theta. Okay, so and then you finally reduce it to this. So you get an exponential of the A theta equal to I minus A plus A exponential of theta. Now, using any idempotent matrix is exponential, you can calculate this. So what did I tell you? What we're going to do is convert that matrix that we see into an idempotent matrix. So that can be done if we divide by a theta. Okay, so let me say A is the idempotent matrix. Okay, and M is the matrix that we have. Now, if I divide M divided by 3 and equate it to A, then I can use this value of M by 3 in this. Okay, so wherever there is an A, I put up an M by 3. Now, what I will do is I will take a 3A equal to M. Okay, so I need to find the exponential of M. E power M is what I want to find. Okay, so if I substitute this as 3A over here, okay, M as 3A, I know that the value of theta is going to be equal to 3. So what do? I end up doing an I minus A plus A e power 3. Okay, because here theta is basically given as 3 when I compare it. Okay, now what do you end up doing? You have to substitute your A as M by 3 so that you can find out e power M. Okay, so let's just look at that part. Okay, I'm going to be using this formula and finding that out. Okay, so you look at the matrix M, it can be written as your projector or your idempotent matrix. Okay, so this is the matrix, looks like this projector, and you can divide it by a 3 to make it a projector. So you divide it by 3 and you make it a projector. Okay, and then what do? You compare it with the formula that you have, and you see that theta is 3. So you substitute 3 for over there instead of theta, and then you compute your exponential of m, because 3a is m. Okay, 3a is m, so you find out your exponential of m. Instead of a, you just substitute the value of you substitute in terms of the matrix that is given to you, m by 3. So that's the final answer that you have. It's option A. Okay, so let's just go back and look at the question that we have. It's option A. Okay. Okay, so let's move on to the last question that we have. Okay, so okay, we have about 2 more questions. This is not the last question. Okay, so the unbiased dice is thrown 3 times successively. The probability that the number of dots on the uppermost surface add up to 16 is, okay. So let's just consider one die. Okay, so if you consider one die, your sample space is basically 1, 2, 3, 4, 5, and 6. Now you've also done where you have rolling 2 dice. Okay, so that's 1, 1, 1, 2, and so on, and then you end up getting a 6, 6. Okay, so that basically has, here you had a 6, here you're having a 36. Okay, so the number of elements in your sample space is 36. Here you just had a 6. Now here they're asking for 3 dice. Okay, so you basically have 3 dice. So they want to know what is the probability that the numbers of the dots on the uppermost surface add up to 16. Now what you're supposed to be doing is, you will of course know that it's going to be 1, 1, 1 to about, let's say 30, wait, you have 6, 6, 6. Okay, so how do I compute the sample space? I multiply 6 into 6 into 6. That should give me 216. Okay, now what have they asked me to do? They want me to look at the number of dots on the top. Okay, so each of these die will have some kind of a dot right on the top. So basically it's going to be 2 or 3 or 4 that's going to be facing that. Okay, so now what do? I take something like, let's say 6, 6, and 6. Let me add this up and check how it's going to be. So 6 plus 6 plus 6 is equal to what? 18, right? Now let me subtract one of them. So 6, 6, 5 is what? 17. Okay, let me subtract another thing. Okay, so 6, 6, 4 should give me 16. Now what I can do is I can push this up to 6 and I can reduce these by 1. Okay, so 5, 5, 6, I can do that. So that should also give me 16. Now if you look at any other combination, you will either see it is lesser than 16 or greater than 16. You never get a 16. But these 3 things, these 3 themselves can be arranged in 3 different ways. So I can have 6, 4, 6, or I can have 4, 6, 6. Over here I can have 5, 6, 5, and over here I can have something like, let's say 6, 5, 5. Okay, so these themselves can be arranged in 3 different ways individually. Okay, so that means I end up having 6 different ways of getting 16. Okay, divided by, you had a total number of elements in the sample space is 216. So if I cancel that, I should get something like 1 by 36. That's option B. Okay, so yeah. So this is the sample space. Okay, so these are the total number of ways in which your 3 dice can be arranged. And then you have 216. So this is what you have. Okay, so what a way you try to add, you never get 16. So these 3 combinations can be arranged in 3 ways themselves. And this is the final answer that you have. So you have 6 divided by 6 into 6 into 6. That's 1 divided by 36. Okay, so let's move on to the next question that we have. The generating function f of x comma t. Okay, so this is the generating function for the polynomials that is given to you, f of x comma t. Okay, what you basically do is you expand this in the first set of terms, or the first order of t gives you the first order polynomial, the second order of t gives you the second order of polynomial, the 0th order of t gives you the 0th order of your p, or probably your p0. Okay, so that is an extensive, like a hugely humongous task to actually do this. Okay, so what I realized is either you can by heart the value of the polynomial that you have, the what is it called? It's called the Bonnet's recursion formula. Okay, you can by heart the recursion formula, or what you can do is you can use the Rodrigues formula to actually find it out. Okay, so the Rodrigues formula is easier to remember than the Bonnet's recursion formula in my personal experience. So I will just tell you how to do it. Okay, so the Legendre polynomials obey the three-term recurrence relation, which is called the Bonnet's recursion formula, and it's nPn of x is equal to 2n minus 1 of x pn. Okay, so this is basically the order of the polynomial. So you're basically writing the nth order polynomial in the lesser orders. Okay, so the two lesser orders that are there. Okay, so and using this recurrence relation, we can find the Legendre polynomials of higher orders. Okay, so now one thing that you have to remember is the two base cases. These are pretty simple to remember. Okay, so if n is equal to 1, then the value of the polynomial is always 1. Okay, so your p0 of x is 1. Okay, and the next one that you have, if n is equal to 1, then the value of the polynomial is always x. So p1 of x is x. So these are basically the seed values. Okay, so you use them in, you call them the seed values because they are the ones that are seeds. Okay, so they help you get the other polynomials or grow the other polynomials from these two. Okay, so these are basically the seed values for your recurrence relation that you have. Okay, so these are all the set of polynomials, your first order, second order, third order. Now if you can remember this value, basically they've asked for your p3 of minus 1. So your x is equal to minus 1 and n is equal to 3. So if you can remember this, okay, if you can remember this entire set, there's nothing like it. But if you can't, let's look at another way to do it. Okay, so okay, so what you're supposed to do is you are supposed to take this, okay, this recurrence relation. If you have to remember this, and then you have to write 3p3 of x is equal to, let's multiply this with 3. So 2 3s are 6 minus 1, which is 5, into, you have an x, p. Let's just remove that into because I feel like that creates a lot of confusion. Okay, so I will put this as an x, and then you have the second order, and then you have a 3 minus 1, which is 2p, and the first order polynomial in x. Okay, so now the thing is that you need to compute 2p, p2 here, p2 of x. Okay, you need to be able to express p2 of x in terms of p0 of x and p1 of x. So that means you have to do 2 steps. Okay, so what I realized is you can avoid the number of steps if you use your Rodrigues formula. Okay, so all you have to do is compute the derivative. I mean, that is a little bit intensive, but yeah, I feel like that is much more simpler to do. Okay, so let's look at that out. Okay, so here you basically compute that. Okay, so you kind of like get this relation from the recursion relation that we have. If you substitute your p2 of x, what you found, you end up getting this, and all you have to do is substitute this, and you get up minus 1. Okay, so you end up getting minus 1. So let's just look at this. Okay, so that's option D that you have there. Now the other way to do this is to use this Rodrigues formula. Okay, so I think I'll kind of like do this right now. Okay, so p 3 of x is equal to 1 divided by 2 power 3 factorial d cubed divided by dx third order derivative, and then you'd have this. Okay, so let me just go back so that I get some space to work on. Okay, and then what I will do is I will have an 8 here because you have a 2 power 3, and 3 factorial is 6, so I'll multiply it that way. Now what I have to do is I need to take the third derivative of this cube that I have. Okay, so I will have to do an x power, let's say this is going to be, what do you have? You have a cube, so you end up having 6 2s are 6, wait, yeah, 3 2s are 6, then I have a 3 here. Okay, and I have an x power 4. Okay, so I think that should be that, and then you have a minus 3, and you have an x squared, right? Okay, so let me just check this out. Yes, somewhere I've kind of like, yeah, okay, so this is a plus, and then have a minus 1. Okay, so now I have to take this derivative. Okay, so I have to do it 3 times. That means I have to do something like 6 into 5 into 4. Okay, so I'm just doing it one shot, into x power, let's say 3. Then let's look at this derivative. So I have a 3 into 4 into 2, and I have an x power that. And this goes away because it's a third order derivative. Then I take this and kind of like simplify it. So let me just cancel this off. Okay, so 6 I can cancel off. And this is basically a 2. So 4 2s are 8. 4 2s are 8. I can cancel off. So I get up 5 x power 3 minus x divided by 2. Is that what I've got? Let me just check. So that's what I'm getting. Okay, so I'm getting a minus 3x divided by 2. I've made some kind of like a calculation mistake, but I think it's fairly simple to do that. Okay, so let's move on to the last question. Okay, so I'd like to like show you how this surface looks later on. Okay, for now let's just focus on what we have. The equation of the plane that is tangent to the surface xyz is equal to 8 at the point 1 2 3 4 is. Okay, let me just move on. Okay, so these are the options that are given to you. I need to find, okay, so I need to find, I have a surface. Okay, I need to find the plane that is tangent to this surface. Okay, so I have a plane that is tangent to this surface, and this tangent is somewhere here. Okay, so this figure is not very nice, but I hope you get the idea. Okay, so let's move on to this. Okay, so how do you obtain a normal to the surface? Okay, so my first idea is to take a surface and obtain its normal. Okay, now they've also given me a point on the surface that I need. They've given me a point on the xy plane, so I'll be using that as well. So now let's look at this. You have a del xyz, y is, okay, so I have to take the gradient of that function that I have. F of xyz is basically given as xyz equal to a constant. Okay, so basically when I take the gradient, I do an xyz minus a constant. Okay, so this constant, when I take the gradient, it's not going to be different. I mean, it's not going to change, so it's still going to give me 0. So I will just ignore that part and I will just take xyz. So once I take the gradient of that, I end up getting yzi cap plus zxj cap plus xy k cap. How do you take the gradient? You just have to do a dou by dou x of xyz, and you end up getting a yz. And then you do a dou by dou y of xyz, and you end up getting what? You end up getting an xz, and so on. Okay, so you have all these. Now let's go on to this. Okay, so the question is to obtain a plane perpendicular to this normal vector that you have. So what do you do? Okay, so you have to compute the dot product and equate it to 0 so that you get the plane. Okay, so you want something that is perpendicular to that normal, actually. Okay, it has to be on that tangent on the surface, and you have to get it perpendicular to that normal. So what do you do? Okay, so I will draw a plane for you. Okay, and I will draw the normal to that surface. Okay, so now what do you have? You have a point on this plane called a P naught. Okay, and you have a point, let's say this is P naught. Okay, and let's say this is P. Okay, and this is P x y z. Okay, now what do you have to do? You have to multiply, you have to take this vector that you have, your n cap, okay, and take a dot product with this vector that you're going to have. Okay, this vector that you're going to have. When you take a dot product, you're supposed to be getting a 0 if they are perpendicular. Okay, so the tangent is basically on that surface. Okay, so what do? You take that and you multiply it with this unit vector that you have. Once you take out the dot product, what do you end up having? You end up having this. Okay, you end up having this x minus 1, because P was written as x, y, z, and this is written as 1, 2, and 4. Okay, so once you subtract them and you take a cross product of that, I mean a dot product of that, what do you end up getting? You end up getting this. Okay, so you multiply them, your I cap and I cap get cancelled. Sorry, your I cap and I cap get cancelled. Not cancelled, it becomes a 1, I dot 1 is 1, j dot j is 1, k dot k is 1, and then you end up getting this equation for the surface that you have. So you end up having 4x. Okay, so I'll take this equation and I divide it throughout by 4. Okay, divide it throughout by 2 actually. Okay, so I divide it by 2, and then you have a 4x plus 2y plus z is equal to 12. So one thing I realized that is that this function called xyz is very common. Okay, so you get it frequently, but until today I had no idea how it looks. So yeah, this is how your xyz function looks. Okay, so you basically have, it's like I think it's like making cubes on all 4 sides. Okay, but it's kind of like open. Okay, so I've never seen this before, and I thought I should show it to you. So basically, this is xyz is equal to 1. Okay, it's extremely hard to imagine it. Okay, so I thought this would be a nice thing to show you. Now, the plane that you got, which was 4x plus 2y plus z is equal to 12. So this is how it's going to come out. Okay,